Today we'll practice the rules we learned in class with exponents and also scientific notation. So our first example, 5x to the fifth times negative 3x squared. Multiply your coefficients first, 5 times negative 3, and then your variables, x to the fifth times x squared. 5 times negative 3 is negative 15, and then we have x to the 5 plus 2, which gives us x to the seventh, for negative 15 x to the seventh. In our next example, the bottom becomes 2 to the fourth times x to the fourth, using our power rule. And when we clean that up, we get 3 over 2 to the fourth times x to the fifth over x to the fourth, pulling our coefficients away from our variables, which gives us 3 over 16 times x to the 5 minus fourth, which is x to the first. So we have 3/16 x. In our next example, again I have like bases. I'm multiplying on top, so that's x to the negative 3 plus 4 over x to the 8th, which is x to the first over x to the 8th. Now that we're dividing, we subtract exponents for x to the 1 minus 8 or x to the negative 7th. We tend to not like negative exponents, so we would write that as 1 over x to the positive 7th, depending on the instructions. In number 4, I have 2x to the 5th times x to the 10th, which is really 2 times 1, x to the 5th times x to the 10th, or 2 times x to the 5 plus 10, just 2x to the 15th. In number 5, I have 1 over 3x to the 8th, which is 1/3 times 1 over x to the 8th. That's 1/3 times x to the negative 8th. In number 6, I have 6x to the negative 5th over x to the negative 3rd. That is 6 times x to the negative 5th minus negative 3, which is 6 times x to the negative 2, or 6 over x squared. In 7, I have 3 over x to the negative 22, all raised to the negative 3rd, which means I raise everything inside to the negative 3rd. So I have 3 to the negative 3rd over x to the negative 22nd to the negative 3rd. We'll follow our rules. 3 to the negative 3rd is 1 over 3 to the 3rd. X to the negative 27th times negative 3 is positive 66. We'll clean up the fraction. So I have x to the 66th over 27, or 1/27th x to the 66th. And for our last one, we have x to the 2n times x to the 3rd. Here, all you can do is show the addition of those exponents, x to the 2n plus 3. Okay, so you also need to be able to work your rules backwards, and you'll have problems like 9 and 10 very often. This tends to be harder because we're often not expected to do this. So here we're told x is equal to 3 to the a plus 1. We need to understand that that came from a like base of 3 multiplying a 3 to the a and a 3 to the 1. Well, we're told also that 3 to the a equals y. So I'm going to replace 3 to the a with y. So x is equal to y times 3. And the question says express y in terms of x, which means get y alone with an x in your answer. So what I need to do here then is divide by 3, and y is equal to 1/3 x, or x over 3. Similarly, with number 10, I have x equals 25 to the b plus 1. Well, again, you need to understand that that comes from 25 to the b times 25 to the first. Now the problem is using base 5. And so I'm going to need to change 25 to the b to 5 squared to the b, because 5 squared is 25. That's still being multiplied by 25. Again, I'm paying attention to the fact that I have this 5 to the b that's my goal, so that I can replace it with y. Well, 5 to the 2b is 5 to the 2 times b, using my power to a power rule, or 5 to the b squared. Order of multiplication does not matter, so I can switch up those exponents. And here, now I have 5 to the b, which is y. Now I forgot my squared term the first time through this, so that's really 5 to the b is y, but that's squared. So I should have y times 25, y squared times 25, or 25y squared. Hopefully you caught my mistake. Okay. So we can apply properties of exponents to verify identities. Remember, an identity is a statement that's always equal. So what I'll do is I'll work on my left side to make it look like my right side. So I have 2 to the n plus 1, which is really 2 to the n times 2 to the 1. And that's over 3 to the n. Well, now I have both 2 and 3 raised to the n. So I'm going to work my power rule backwards and rewrite that as 2/3 all to the n. And that's times 2 to the first. Now when I clean that up, that's equal to 2 times 2/3 to the n. And suddenly I've proven my identity. We'll work the same one in a similar way. So here I have 3 to the n plus 1, which is really 3 to the n times 3 to the first, minus 3 to the n. Well, here's that seeing structure and expressions, and recognizing that I have a 3 to the n that's a common factor on both parts of my minus sign. So I'll factor out that common 3 to the n, which leaves me with 3 to the first minus 1. Cleaning up parentheses, 3 to the first is 3, 3 minus 1 is 2. So now I have 3 to the n times 2, which is the same as 2 times 3 to the n. Finally, I have 1 over 3n all squared times 4 to the n over 3. I need that to end up looking like 1/3 times 2/3 all to the 2n. So I rewrite my 1 over 3n to the second is 1 over 3n times 2, and that's still times 4n over 3. So I'm going to pull my coefficients together, and I'm going to rename 4 as 2 squared. And I rearrange that n times 2 as 2 times n. So I really have 1 over 3, order of multiplication doesn't matter, so 1 over 3 to the 2n times 2 squared to the n all over 3. Again, keeping in mind that order of multiplication doesn't matter, I can move the 3 to the first that's on the bottom of the second fraction off to the left. So I have 1/3 times 2 to the 2n over 3 to the 2n. And now that both 2 and 3 are raised to the same exponent 2n, I can rename that as 2/3 all to the 2n, working that power rule backwards. And I've proven my identity. Okay, so the last thing we need to review is scientific notation. Remember, when you have a negative exponent on base 10, that means it's a small number and you move your decimal left that many places. And you fill in all your gaps with zeros. So 73 times 10 to the negative fifth is equal to 0.00073. If you have a big exponent, or a whole number, positive exponent, that means a big number, which means move your decimal that many places right. So 7.3 times 10 to the sixth is equal to 73 with 5 zeros, or 7,300,000. Now you have to work backwards as well. So if you're given a number written in scientific notation, you move your decimal back, so it's a number between 1 and 10. You count how many places back you went, write your new number between 1 and 10, and it's times 10 to the number of places you moved. So 2.34000 is 2.34 times 10 to the fifth. I lost a 4 there. Make sure you get that in there. 0.0035 is a small number, so it needs a negative exponent on 10. 3.5 times 10 to the negative third. My next one's a big number. To change it to 5.321, count how many times I moved my decimal, times 10 to the eighth. And finally, you'll have to pause for this last one when I move it up. That really small decimal is 1.2 times 10 to the negative 9th. Again, we can use our rules to simplify scientific notation problems. So in number 1, I have 2.4 times 10 to the 20th plus 4.5 times 10 to the 21st. Here I'm adding. So I need those base 10 numbers to have the same exponent on them. So 2.4 times 10 to the 20th I'm going to leave alone, but I'm going to change 4.5 to 45 times 10 to the 20th instead of 4.5 times 10 to the 21st. Now I can add 2.4 and 4.5 because I have a 10 to the 20th that's like a common factor that I can pull out. And clean up the inside. So 2.4 times 45 is 47.4 times 10 to the 20th. But that's not good form, so I need to call that 4.74 times 10 to the 21st, since I moved that exponent back over 1. Now in number 2, be careful, we're not adding, we're multiplying. So we'll multiply our whole numbers, 7 times 5, and our base 10, 10 to the negative 7 times 10 to the 5th. 7 times 5 is 35, and then we have 10 to the negative 7 plus 5, which is 35, times 10 to the negative 2, which means move my decimal, 3.5 times 10 to the negative 3, sorry. That was a negative 4, sorry, negative 5. 3.5 times 10 to the negative 5.